In this lecture, I am going to talk about how to get the various moments of a random variable from the transforms, that is the moment generating function. Also, it is called the characteristic function of a random variable. The reason behind the alternative name moment generating function, in short it is called the MGF, is that the moments of a random variable are easily computed once a formula for the associated random variable is available. Okay, so you have a random variable. For this random variable, you define its probability density function if it is continuous, or you may have probability mass function if it is a discrete random variable. From this, you find the moment generating function. Sometimes people also called characteristic function. Characteristic function of a random variable. Either way you can call it. And this moment generating function is denoted by m sub x of s, or some other authors denote this by phi x of omega or theta of t. Now in this lecture I am going to consider this notation. Okay, so now once you know this moment generating function, and from this I can easily compute various moments. Various moments of the random variable. So when I say moment, it is defined as follows. We have first order moment, moment, and it is denoted by mu sub 1. It is defined by expected value of x to the 1. And we have second order moment, it is denoted by mu suffix 2. This is expected value of x to the 2. Similarly, you can define the third order moment. This is denoted by mu sub 3, which is expected value of x to the 3. Similarly, you can define various moment. Let's say kth order moment. So this is denoted by mu sub k, defined as x to the k. Okay, so these are various moments. Now if you notice, the first order moment is the same as mean of the random variable. And now again, if you notice a little bit in this, if you take the first order moment and the second order moment, we can compute variance of the random variable. So variance of x equal to e of expected value of x squared minus expected value of the x whole squared. So once you know the first order moment and the second order moment, you can calculate the variance of the random variable, that is mu 2 minus mu 1 whole squared. Therefore, it is very easy to calculate various moments once you have the characteristic function of the random variable or moment generating function of the random variable. So the moments are very important, but computing moments directly sometimes takes a lot of time. So whenever you want to calculate moments directly, it may involves a lot of time. It makes you to spend a lot of time. Takes a lot of time, and sometimes tedious and cumbersome also. Therefore, the concept of characteristic function is useful. Okay, now let me define the characteristic function. Okay, and from that let us see how we can calculate the various moments. As I said, the characteristic function is denoted by m sub x of s. So it is defined as expected value of e to the sx. And this is a capital letter, it's a random variable. It is a random variable, and you can think of this as g of x, and we know how to find the expected value of g of x. So it is going to be like integral of e to the sx, the density function of the random variable fx of x times dx. So the density function is multiplied by the e power sx. Now this is a definition of your characteristic function or moment generating function. Now let me show you the usefulness of this characteristic function, how it is useful, and how one can derive various moments of the random variable. Once you know the moments, then you can describe the random variable, right? So that is a whole purpose we are doing this exercise. Now if you look at this this one, there is an exponent. This exponent can be expanded. So we know that e power x is equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on. Let's say x to the k over k factorial plus and so on so forth. In the same manner, this also can be expanded, and in general the limit is from minus infinity to plus infinity. So this is going to be integral of minus infinity to plus infinity, and e power sx is going to be 1 plus sx by 1 factorial plus sx the whole squared by 2 factorial plus sx whole cube over 3 factorial, correct? Then dot sx whole to the k over k factorial plus go on. The whole thing is multiplied by your density function fx of x times dx. Now bring this density function inside, then this is going to be integral of fx of x plus sx times fx of s by 1 factorial plus sx the whole squared over 2 factorial times fx of x plus sx whole cubed over 3 factorial times fx of x plus dot plus sx whole to the k over k factorial times fx of x and multiplied by dx. Now bring this integration inside. So this is going to be integral of minus infinity to plus infinity, integration over the limit fx of x times dx plus integral of in this s times x times fx of x into dx by 1 factorial plus integral of s squared x squared by 2 factorial fx of x plus integral of s cubed x cubed over 3 factorial times fx of x plus dot plus integral of s to the k x to the k over k factorial times fx of x into dx. I forgot to put a dx here, and here also I put a dx. Okay. Now if you look at in this expression, this is going to be 1 by normalization property of the random variable density function. Okay, so that is going to be 1 plus, and in this one it is a constant. Why is it constant? Because the integration is with respect to x. Therefore I can pull out of the integration. So s times integral of x times fx of x times dx. Maybe I can put 1 factorial outside, plus the second one, this is a constant, therefore a squared over 2 factorial integral of x squared times fx of x. For all this integral, the limit is from minus infinity to plus infinity. Plus s cube over 3 factorial integral of x cube fx of x into dx plus dot dot plus s to the k s to the k over k factorial integral of x to the k fx of x times dx, and the limit is from minus infinity to plus infinity. That's all integrals. Now if you notice in this is the same as the expected value of e of x, and this one is going to be second moment, and this one is going to be the third moment of the random variable, and this one is going to be the kth moment, plus keep on goes. Therefore this is going to be 1 plus s times e of x plus s squared over 2 factorial times expected value of x squared plus s cube times 3 factorial times expected value of x cube plus and so on. Expected value of, this is s to the k over k factorial times expected value of this is x to the k, and it keep on goes. So this is my characteristic function of the random variable x. So the interesting thing is that the characteristic function has all the moments embedded in it. See, the mx of s has all the moments embedded in it. Embedded in it. So you can look at here, you can get first order moment, then second order moment, third order moment, and so on. This is kth order moment. So all moments are there in this moment characteristic function or moment generating function. So you can compute the moments from the characteristic function. Now in this you are, let me call this is equation number 1. Now put s equal to 0 in this. So what will you get? mx of 0 is equal to 1 plus, in the second expression, if you look at here, the e of x is multiplied by s. Therefore if you substitute s, then it is 0 and 0 and 0 and so on, all zeros. So therefore it is going to be 1. mx of 0 equal to 1. Okay. Now if you take the derivative of m sub x of s with respect to s, so d by ds of mx of s. So the first term is 1, so it is going to be 0 if you look at here. And what about the second term? Second term is s into e power sx, s times e power x, s times e of x. So this is 1 times e of x, and the second term is going to be if you look at here, this s squared becomes 2s, so 2s times e of s over 2 factorial plus 3s squared over 3 factorial times sorry, this is e of x squared, e of x cubed plus dot 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 plus s power s to the k, that is k times s to the k minus 1 divided by k factorial times expected value of x to the k. So this is going to be, now you substitute s equal to 0 in this derivative. Now what will happen? Maybe I can simplify this before that. So you'll get e of x plus 2 factor will get cancelled, s times e of x squared plus 3 and 3 factor will get cancelled, therefore s squared over 2 factorial, then e of x cubed plus this is s to the k minus 1 divided by k minus 1 factorial times expected value of x to the k. So now substitute s equal to 0, d by ds of mx of s, substitute s equal to 0, then what will happen? Yeah, the first term will come as it is, e of x, and the second term is going to be 0, third term also going to be 0, plus all the terms will become 0. So finally you'll get e of x. What is this e of x? E of x is the mean of the random variable. Therefore the first moment will give you the mean of the random variable, that is you take the moment generating function, differentiate with respect to its parameter s, and then substitute s equal to 0. Therefore d by ds m sub x of s, after that you substitute s equal to 0. So this is a formula to calculate the first order momenta. First order moment, or also it is called mean of the random variable, mean of the random variable x. Now you continue this process. Let me differentiate one more time this d by dx. So d square over ds squared, then f sum m sub x of s, which is equal to, if you look at here, then this one becomes 0 plus s times e of x squared, s becomes 1 times e of s squared plus the s squared by 2 factorial becomes s times 2s by 2 factorial e of, I'm sorry, this is not x squared, that is e of x squared, then this is e of x cube plus keep on goes, then plus k minus 1 times k s to the k minus 2 divided by k minus 1 factorial, k minus 1 factorial times expected value of x to the k. Now again substitute k s equal to 0 in this expression. So d squared over ds squared mx of s, substitute s equal to 0, then this is going to be e of x squared plus rest of the terms are going to be 0. So this is going to be 0, this is going to be 0, all terms will become 0. So plus 0. So this is your e of x squared. So if you differentiate 2 times and substitute s equal to 0, then you will get a second order moment. E of x squared is equal to second derivative with respect to s of m sub x of s gives the second order momentum. Excuse me. Second order momentum. Fine. So you can continue this process, and let's say you can take the derivative k times k times. So the first term, second term, third term will turn out to be constant, and that will turn out to be constant, and some terms will become 0. Okay, and then substitute omega equal to 0. So then what will happen? All other terms will vanish other than the expected value of x to the k. So therefore x to the k equal to kth derivative of the moment generating function mx of s. So in this way one can calculate various moments of the random variable. And one more mistake I did in the beginning of the lecture itself. So what I said is, sometimes you can use this notation also. So in this way, your phi x of omega, sometimes author defines like this: expected value of e to the j omega x. Okay, so people will write like this, where s equal to j omega. S equal to j omega. Okay, so then the formula changes a little bit, but anyway it's one and the same. Okay, either you can use m sub x of s. So m sub x of s is called the moment generating function, and phi x of omega is called characteristic function. Simple slight modification, that's it. Okay, nothing changes actually. Either you can use this formula or this formula, but if you use a characteristic function, this phi x of omega, then what will happen? You have additional factor, that is 1 by j, 1 by j square, 1 by j cube, like this. That means your e of x equal to 1 by j times the first derivative with respect to omega of phi x of omega, and the second order moment is given by 1 over j squared times the second derivative with respect to omega of phi x of omega. Then it keep on goes. Expected value of x to the k, that is kth order moment, is going to be 1 over j to the k, 1 over j to the k, d kth derivative divided by d omega k phi x of omega. And remember, this all are evaluated at omega equal to 0. This also evaluated omega equal to 0, and this also evaluated at omega equal to 0. So in this way one can calculate various moments of the random variable from moment generating function. So instead of going through this lengthy exercise, one can find the moments in a shortcut method. I mean this formula. Like we know that the moment generating function mx of s equal to integral of e to the sx times fx of x times dx. And the whole exercise I showed here is in order to show that this moment generating function contains all the moments. So that for that purpose only I have done this derivation. Now let us find this using one or two steps. Now take the derivative of both sides. So d times mx of s over ds, which is equal to, you are differentiating with respect to s. So x is constant. Therefore d by ds of integral of e power sx times fx of x times dx. So then what will happen? This e power sx is the same as e power sx. Once you differentiate it, then if you differentiate the exponent, then it will become x times e power sx times fx of x into dx. So this is the first derivative, d by ds of m sub x of s. Now substitute s equal to 0. First derivative ds. So So this is going to be x times e power 0 fx of x into dx. So this is again I can write as x times fx of x into dx. By definition, this is going to be e of x, the first moment of the random variable. Similarly, I can differentiate 2 times, then I'll get the second moment. And if I differentiate k times the function m of s with respect to s, then I can get kth order moments. So d to the k over ds to the k times m sub x of s is equal to integral of, when s equal to 0, then this is equal to x to the n fx of x times dx. So this is nothing but the expected value of x to the k. X to the k. So this derivation involves an interchange of a differentiation and integration. The interchange turns out to be justified for all of the applications to be considered in this lecture. And moreover, the derivation remains valid for a general random variables, including discrete ones also. The same process can be applied, same differentiation is also applied to the case where the random variable is discrete. So it could be carried out more abstractly in the form like as follows. Like we know that m sub x of s equal to expected value of e to the sx, right? So differentiate ds of mx of s equal to, you differentiate this. If you differentiate, you can take the differentiation inside the expectation operation. If you take inside, then this is going to be expected value of d by ds times e to the sx. Now s is a x is a constant random variable, so expected value of x times e to the sx, and again you have x here, so that again you'll get the same conclusion, same formula. Okay, so the whole purpose of this lecture is to show that your moment generating function contains all the moments, like first order moment, second order moment, third order moment, and so on. So from that moment we can find out the various parameters which are needed for our random variable. Like we can find out the mean of the random variable, then we can find out the second order moment. Once you know the second order moment and the first order moment, then you can find out the variance of the random variable. As I said, your variance of x is equal to e of x to the 2 minus the first order moment squared. So this is mu2 and this one is mu1 squared. So once you know these two moments, first order moment, this is the first order moment and the second order moment, then you can find out the variance of the random variable. So this is very useful one. Therefore the transform or the moment generating function is a very important concept for our random variable to calculate its various parameters. So at this point let me stop. In the next lecture I will come up with some examples. Thank you very much.